now doing, now it works?
Yeah, perfect.
Okay, so go back. Okay, so this was the second slide, which you have not seen, when I was just talking about different types of systems, and now about the vibrational effects. So we have the harmonic and anharmonic approaches, but we know that in reality everything is really anharmonic. So in my talk, I will start from very briefly introducing theoretical and computational framework, and then I will take some time to show you different comparison between spectra for the various systems, trying to convince you why we need to include vibrational effects and why we need to include anharmonicity. This is, of course, very often known, but I will just show you some specific examples when it will be maybe more visible than usual. And then I will spend some time on the specific aspect of astrochemistry and applications for astrochemistry of different computational spectroscopy models. So talking about the theoretical framework, I just said I will do it very briefly because there is nothing new. Most of the computations were done by the available software. So when we are thinking about the computations of the broad range of the spectra, so here I'm showing between microwave and photoelectron spectra. So in particular, if we go from the mid-infrared toward higher energies, we are first including the directly vibrational spectroscopy. And when we are going beyond it, when we start to moving to the electronic excitations of different electronic states, we are starting to have so-called vibronic spectra, so the vibrational overlap between the two electronic states. So this is essentially using this two theoretical framework, so vibrational computations and vibronic computations, we can simulate a broad range of spectra, and in principle, we could be able to simulate this whole range. So what are the main approximations? We always deal with the Born-Oppenheimer approximation. So even if we are calculating a lot of different, say, spectrum in the broad range, in each case, it is just two potential energy surface at the time. So each potential energy surface is calculated separately, and the transitions are always just between the two potential energy surfaces. For vibrational spectroscopies beyond harmonic model, I will be always showing a general vibrational perturbative model as developed and implemented in Gaussian by Julien Blondeau and Vincenzo Barone. So this allows to calculate vibrational energy levels, so transition energies, and also transition integrals, so band intensities. And it can be implemented for infrared Raman, BCD, and ROA. For vibronic transitions, we can have Frank-Condon and Herzberg-Teller approaches, adiabatic and vertical models for harmonic potential energy surface, mode mixing, Dushinsky effect. But despite that the vibronic model itself is within the harmonic framework, in most cases, I will be having some anharmonic corrections just for the positions of the band in both ground and excited states. From the point of view of computational strategies, so QM, electronic structure calculations, in my opinion, the most efficient way, but it was also seen here in most of the talks, is to use some combinations of the approaches. So we always are able to perform single point computations and much higher level of theory than anything else. So this can be done for relative energetics, for example, of conformers, or for vertical energies, so the pure electronic transitions, energies in transition moment. Then some higher level of theory can be used to calculate say the equilibrium properties and harmonic frequencies, properties at the bottom of the well. And finally, the lowest level can be used for anharmonic corrections, which will be the most expensive calculations. And what I would like also to highlight that sometimes the the need of using different combination of different methods is not only because of the computational cost, but also because of the properties which are available at some QM models. So properties are often not available at very high accurate models, or even something like double hybrid functionals. So switching to showing you some examples if we think about accuracy of energies and of wave numbers in the ground state, we can combine harmonic and anharmonic computations at different levels. And here's the case of oxyran when we of methyloxyran, for which we can see how we are improving accuracy, moving from just DFT represented here but by pretty LYP, MP2 to double hybrid functionals, and to the case when harmonic part of the potential is corrected by couple cluster with actually best estimated using also composite schemes, including complete basis set and Corvallis correlation. So we can see that we can, with these approaches, we can reach something like below 10 reciprocal centimeters mean absolute errors and maximum errors of about 20 or below 20 reciprocal centimeters. If we use this kind of, here it will be a couple cluster with double hybrid functional. If we compare directly with experiment, you can see in this part of the mid-infrared spectrum, you barely see the difference actually. So experiment is with black dots, which are somewhere here. So the accuracy is clearly very good. And what is also interesting, but in this slide, I would like to highlight that it's not only needed to have one quanta, so the fundamental transitions, which are represented by green lines also here, but also two quanta, so overtones combination band, or even three quanta transitions to get the fully anharmonic spectrum, which can represent best the experiment. And this is, of course, very much, let's say, this is necessary in the spectrum ranges when we don't have fundamental bands at all. So here it is represented by this range about 1,750, but it is also, for example, the whole near infrared range when we don't have fundamental transitions at all. So if we want to have any spectral simulations, we need to go beyond harmonic approximations and have anharmonic intensities. If we go to look at the non-fundamental transitions, they can be actually also very intense. So this is the case of uracil, which has the Fermi resonances. And if we take the harmonic, even harmonic scale, we have just two strong bands in this region. If we move to the best anharmonic model, we can represent this very complicated pattern with some very strong transitions, which are comparable in intensity to the fundamental ones. This type of, I don't know why it's jumping, but this type of calculations can be done not only for infrared, but also for VCD, Raman, ROA. And this is again the example of methyloxyran showing good agreement for all of these spectroscopies. If we are moving to the simulations of electronic spectrum of any type of electronic transitions, here I'm showing the spectrum in the very broad energy range from 4 to 11 electronovolts, so encompassing a lot of different electronic transitions. And if we do the calculations of vertical energies, which are here represented in red, it is really difficult to make an assignment and to say really which transitions is where and which excited states at all we are observing. So does each of these peak is some electronic transition or some is not? So it's very, very, very difficult to make some accurate assignment in such cases. When we switch to the vibronic computation, as here is enlarged this small part, we can actually really obtain the energy profile in quite accurately. So this can also help to answer the question how many electronic states we have within one band. So in this case, in this complex band, it was needed to have 2 electronic transitions to obtain the good match with experiment. We always want to compare computations and experiment, and often we compare lambda max with vertical electronic energies, which might not be the good idea. This is one of the examples when the lambda max is about something like 0.4 electron-volt. Vertical energies and TD-CAM and AOM are somewhere here. But if we use just TD-CAM, B3LYP and simulate actually the spectrum, we can get the good agreement. So the problem is that when we are comparing vertical energies with lambda max, sometimes lambda max has very little to do with vertical energies. So with this, I will move to the computations for astrochemistry, which are kind of important. I will introduce a little bit more about astrochemistry because I think it's not a very common topic for this audience, but I think it's very interesting. So whatever information or most of the information which we are having is measurement of some absorption, emission of light. So it's again light matter interactions in different environments, and astrochemical environments can be interstellar medium, but it can be also planetary atmospheres or planetary soil when we can also access. And it covers really all the types of radiations from the radio, infrared, visible, ultraviolet. And the problem is that we don't know what we are measuring. So the systems are unknown and inseparable. So we need to compare with different databases and have as much reliable and accurate data for comparisons. So actually, up to now, almost around 250 molecules have been already detected, even in the interstellar medium. And these molecules can be such big or important kind of organic molecules like methyloxyran, which was the first molecule discovered in the interstellar medium, or some aromatic molecules, including nitrogen. So this really shows us that the complexity, what can be found, is quite large. And this is why it's the big interest of prebiotic molecules to understand how the life came to Earth. Did the prebiotic molecules arrived on the meteorite, or it was created from on Earth itself? So the detection of biomolecules in interstellar medium and some planetary biosignatures is a very, very, very hot topic. And I will just highlight that so far the pyrimidine was, and from the DNA basis, pyrimidine and uracil was confirmed to be present in meteorites as the extraterrestrial, and the glycine was, and some other amino acid was also confirmed. But none of this molecule was so far confirmed in the interstellar medium. So the computational support for the astrochemical studies is becoming actually quite important. And so far, most of the molecules, especially in the interstellar medium, have been detected by radio experiments, radio measurements. But nowadays, we see increasing importance of vibrational fingerprints and vibrational spectroscopies, which will be related to mid-infrared spectrometer on James Webb Space Telescope. And we have also now Mars robotic missions and some instruments on board. For example, Perseverance Mars rover in Mars 2020 was including also infrared, like for example, infrared. So our support is to support laboratory experiments which are made to make direct comparison with some experiments from astrochemical environment, but also eventually provide missing data which is not yet available or available at different conditions or extend energy ranges and so on and so forth. So one of example of such practical analysis is this analysis of Mars soil, which is ongoing analysis from the probes taken by Perseverance rover and the near-infrared instrument on board of Perseverance rover. So me with my PhD student Teresa Fornaro, still from the Scuola Normale Superiore in Italy. She's now working as a scientist in this Mars 2020 program. And she's experimental scientist doing different Mars soil examples and need to assign the data, need to analyze the data. And in particular, near-infrared spectra are very difficult to assign because there is little known about it. So we collaborated to make some assignment based on the computations which she's after using to compare with the samples from the Mars. Talking about nucleobases in astrochemical environments, so we know now that complex organic molecules can be formed from very small molecules such as water, ammonia, and so on in upon UV irradiations at 10K, so not even from bigger molecules, but such small. One of the projects we have done was just as an example to show what can be performed for DNA bases and how computational spectroscopy can assist astrochemical environments. And example was time in molecule. So we aimed at predict to spectra which is not actually available experimentally and can support either further laboratory studies or directly astrochemical studies. So if we think about atmospheres of exoplanets like Titan, Saturn, some of interest is mid-infrared spectrum. And for example, missing there is no measurement for time in cation infrared spectrum. If we think about detection of molecular biosignatures, but near infrared, even timing, neither timing nor timing cation, there is no experiment. And in the case of photoelectron spectra, there is either missing resolution or is missing energy range. So there is spectrum in very small energy range is high resolution and a larger energy range is lower resolution. So the computation have been done by this GVPT2 model using hybrid, double hybrid plus hybrid functional for both neutral and cationic timing. So these are both ground state. So it is kind of easy, and vibrational results photoelectron spectra was calculated by adiabatic Hessian-Frank-Condon model, plus anharmonic corrections coming directly from this GVPT2 calculations. Adiabatic energy itself was taken from the previous study by one of my collaborators, Majdi Hochlaf, who was also collaborating on this paper. And it was done by Kapu cluster level with F12 basis set. So if we look at the spectra of infrared spectra, for what we can compare with experiments, so the timing, which we have some experimental data, we are getting very good agreement within 7 reciprocal centimeters, not only for fundamental bands, but also for all observed transitions, including overtone. And we can get realistic shape for this energy range, which is related to the Fermi resonances. So it is again similar case like Uracil, of course, when we have essentially 2 intense bands at the harmonic level, 2 intense fundamental transitions, but the experimental spectrum show many more bands, and this can be reproduced by anharmonic calculations. So what we can say based on comparison of these computations, that first of all, that the spectrum of natural timing and cation is pretty different. So if we want, we can distinguish between these 2 species. And it is not only in the mid-infrared, but also in near-infrared. And we can eventually compare it with some spectra coming from different sources, like here's example of the spectrum of the Titan atmosphere, so-called Titan tholins, and we can ask ourselves questions whether the timing can be present or cannot be present in this environment. Based on this picture, I would say that we cannot exclude it fully, but we cannot. Definitely, a lot of other molecules are needed to explain this spectrum. If we go to the photoelectron spectrum, we can compare with experiment in the broad energy range, which is here I'm comparing the shape, which you can see that the experimental shape is quite broad. One from the computations, we can get the stick spectrum, so we can have more detailed analysis. And if we compare the peaks which have been observed in this energy range, also at a higher resolution, we are getting the agreement within 12 reciprocal centimeters in case when we compare relative band position, so the band's position relative to the 0-0 energy. But the 0-0 transition itself is in agreement within 0.02 electronvolt. This is also showing very good agreement, and we can make similar simulations for different temperature just to oh, I see. Do you hear me? We can do these calculations also in different temperature, and so like mimic different types of astrochemical or any other hot and cold environments. To conclude that we have tools which allow reliable predictions of vibrational effect for a wide range of rather small but semi-rigid and flexible systems, and we predictable accuracy of weight numbers and well-established hierarchy of models. And as for intensities, we can have accurate quantitative infrared intensities, and most importantly, also non-fundamental transitions. And for electronic spectra, we can obtain the realistic band shape. I'm highlighting here some review articles which related to astrochemistry, tutorial review about vibrational vibronic computation, and this very recent introductory review about very general about computational molecular spectroscopy, which is a good collection of references mainly. And in this, I would like to acknowledge my